Hi, and welcome to this lecture, Introduction to EFM32 API. In this lecture, we will learn how to control the EFM32 peripherals and how the API is built up. The EFM32 API has two layers. The lowest layer is called CMSIS and is a direct mapping to the peripheral registers. CMSIS stands for Cortex Microcontroller Software Interface Standard, and this is a vendor-independent standard which is defined by ARM. On top of CMSIS, MG has built a peripheral library which we call emlib. Emlib provides a higher level of abstraction and a simpler application interface. A developer is free to choose either one of these interfaces or even mix and match between the two. We will start by discussing CMSIS and how the peripherals are accessed from software, and then move on to emlib and its documentation. All peripherals on EFM32 are memory mapped. Controlling the peripherals are done by reading and writing to certain addresses in memory. In the reference manual, we can see that peripherals have their own section in the system address space. Inside the peripheral block, each peripheral is given its own memory region. For example, here is the memory region reserved for the ADC. The bottom address is called the base address for that peripheral. The interface to a peripheral is composed of several registers. Each register is 32-bit wide and located in the address space for that peripheral. On this slide, we see an overview of the registers that control the ADC on Giant Gecko. The left column, called offset, shows where the register is located relative to the base address. The actual address of a register is the sum of the base address and the offset. In software, we need some convenient way to reference these registers. On EFM32, this is done in the form of Peripheralstructs. For each peripheral, there is a defined struct which includes all the registers for that peripheral. Struct pointers are mapped to the corresponding peripheral base address, and the registers are defined according to the offset. Here's an example on how to use CMSIS. The first line of the example on this slide sets the compare 0 register of the RTC. The second line reads out the current value of the RTC counter. Most of the time, we're not interested in the full value of the register. Rather, we want to modify individual bits. The names and descriptions of registers and the bit fields are found in the reference manual for each device family. On this slide, we see the ADC command register. Writing a 1 to bit 0 in this register will start a single conversion. Here is how we could write this by using CMSIS. Note that the peripheral and register directly follow the names given in the reference manual. On the right hand side, we see a constant which is also part of the CMSIS library. This constant have bit 0 set to 1 and all other bits are 0. The naming convention for these constants also follow the names given in the reference manual. So expressions like this can quickly be written by reading the register descriptions in the reference manual. When setting an individual bit in a register, you should make sure you do not unintentionally clear other bits in that same register. Common method to ensure this is to OR the bit mask you want to set with the original register contents. Clearing a bit is done in the same way by ANDing the register contents with an inverted bit mask. Some registers contain bit fields which span multiple bits. For these bit fields, there are also constants defined for the values of the bit fields as well as masks where all the bits in the bit field are set. For instance, the DAC control register contains a 2-bit wide field which sets the conversion mode. The possible values for the conversion mode is found in the register description. This is how we could use CMSIS to set the conversion mode to sample and hold. Note that we first have to clear the bits in the bit field by ANDing the register with the inverted bit field mask. Then we OR in the value of the field. That is it for the CMSIS part. Now we will move on to talk about the Peripheral Library emlib. Emlib abstracts a way to direct register manipulation. The application interface when using emlib consists of functions and init structs. By using emlib, the code for controlling the peripherals can be made simpler and more readable. A typical way to configure a peripheral on the EFM32 is to fill an init struct and then pass a pointer to this struct to the corresponding init function. The first line on this slide declares an init struct and then fills this struct with a default value. Default values are useful when you do not care about all the values in a struct. In this way, they are given sensible default values without the programmer having to specify all of them. The next lines fill in the struct with appropriate values for the application. Note that the values here are enums. The use of enums makes it easy to see what the allowed values are for each field. Not all fields will have enum values, some will also use integers or boolean values. Finally, the call to ADC init signal will set up the registers. The first parameter we pass here is the ADC0, which is actually the peripheral struct that we used in CMSIS. The entire source code for emlib is also provided, so it's easy to see what goes on under the hood or even write your own peripheral drivers based on emlib. The documentation for emlib can be found in Simplicity Studio by clicking the API documentation button. This will open the documentation in your browser, and you click the emlib peripheral API link to jump to the emlib documentation. Expand modules and emlibrary, and you will see a list of modules. Each peripheral is described in its own module. Let's have a look at the DAC peripheral. As you can see, this section lists a number of structs, defines, and enums that are used in the emlib section for the DAC. Then we get to a list of functions. You can click on the function names to jump directly to a description of the function. Here we see the DAC init function, and it has a short description as well as a definition of the parameters and eventual return types. The first argument to this function is a pointer to the DAC peripheral register block. This is the same structure that we use in CMSIS, so this will typically be DAC0. The second argument is a pointer to the DAC init struct. As we can see here, we can click on the type def of the init struct to go to a definition of that struct. Here is a list of all the data fields that are used in the init struct of the DAC. We can click on each of the member names to go to a definition of what they represent. Some of the fields are enums, and we can click on the type def to show the available values for that enum. Here we see the conversion mode enum, and it has the 3 values for the conversion mode that we also found in the reference manual. Similar documentation will be found for all the other peripherals. For instance, here is the GPIO part of the emlib. It has a number of functions to manipulate the GPIO pins. Thanks for watching. For more information, go to energymicro.com.